Hi everybody. So last class we looked at multiple scales equation shown here. When you have an exponent that's 2 rather than 3, and what we've seen is the analysis for this requires two scales, the slow scale and a super slow scale, right? And expanding u in up to 3 terms. Okay, so we've gone through this, and at the end of the day, we've obtained the correction to the phase, and here it is. That's the correction term. Okay. All right. So let me just show you how this comes about. Okay, and why it's important to look at this case. So this is a very typical thing on when you have a generic Hopf bifurcation. And as an example, let's illustrate it on this system here called the bracellator. Okay, so it's a two-component system. It has a steady state x equal to 1, y equal to b. As you can check, just by plugging it in here. Right, so for example, you could just solve these two equations, but just let's double check here. X equal to 1 and y equal to b clearly solves that second equation, and similarly in this equation when x is equal to 1, y equal to b clearly solves the first equation too. Okay, so that's a steady state, and then we compute the Jacobian, and what we find is that the trace is equal to b minus 2. The determinant is 1. Okay. The determinant being the product of the eigenvalues being equal to 1 means that they're either both positive or negative, or both complex conjugates of each other. Okay, so the equation for the eigenvalue, let's recall, is this. Okay, and now here if I set the determinant equal to 1, when trace is equal to 0, then you get lambda squared plus 1 equal to 0, and lambda is equal to plus or minus 1, I, right? Purely complex eigenvalue that corresponds to the Hopf bifurcation. So in other words, when trace is equal to 0, or when b equal to 2, that's when you have a Hopf. Okay. So now what we want to see is what kind of behavior can we expect near the Hopf bifurcation when b is very close to 2, like let's say b is equal to 2.1 or something like that. All right. Now, to do that, we need to linearize around the equilibrium 1b, okay, and with b close to 1. So I will shift the variables for now. So here's a simple shift. Here, plug it into the equation. I get new equation for u and v. And now I'm going to expand this resulting equations around b equal to 2 as follows. Okay. So I will expand b equal to 2 plus epsilon to the square. U is equal to epsilon times capital U, and v equal to epsilon times capital V. Okay. When I plug all of that stuff in, okay, this is what I get. To leading order, I get u prime is equal to v plus u, right? That plus u comes from here. Remember when b is equal to 2. Okay, and then plus some epsilon terms, and then some epsilon squared terms, etc. And v prime is equal to minus v. This comes from where? From here. Okay, and then minus 2u, that comes from here, remembering that b is equal to 2, and then high order terms as well. Okay, so to leading order, we have these two equations. If I just ignore all the epsilon terms, okay? And this corresponds, so basically the leading order system looks like u prime is equal to v plus u, v prime is equal to minus v minus 2u. Okay. That's the leading order equations. And what does that mean? Well, that's actually an oscillator. Okay, so a simplest way to see that is just to rewrite the system as a single equation. So in particular, if I differentiate the equation for u prime, okay, then I get this, and now I can plug in v prime in here, okay, sorry, yeah, and I plug in u prime in here, and what I get is this equation here to leading order. So u double prime is equal to minus u, which is a harmonic oscillator. Okay. Now, if I do the same calculation, but keeping all of the epsilon order terms, and then epsilon squared order terms, then I obtain this equation in green. Okay. And that basically is a harmonic oscillator, u double prime is equal to minus u, perturbed by order epsilon terms which have u squared in them, and then order epsilon squared term which are kind of cubic in nature. Okay? So that's why it's important to know how to handle u squared terms. And so now I expand this as before. So I apply the same technique using multiple scales to this equation in red. Okay? So in other words, I look at u being a function of t, then slow scale s equal to epsilon t, and super slow scale tau equal to epsilon squared t. And as we've done in a previous example, it turns out that the first thing you find is that us, in other words, du by ds is equal to 0. So u is independent of the s scaling. Only depends on the super slow scale. So this is the same calculation as before. I'll skip it. And so we get that u is a function of t, slow scale, t, which is the order 1 scale, and tau, which is a super slow scale of order epsilon squared. Okay. And as before, we again expanded up to third order, u0 plus epsilon u1 plus epsilon squared u2. Okay. And then we write down the equations for u0, for u1, okay, and for u2. Again, I'm skipping all the details here. You can fill this in, but at the end of the day, one has to solve the equation for u1 as well as for u0, of course, and then plug it into the equation for u2. Okay? And one then obtains the following terms, the following secular terms right here. Okay. And setting this stuff equal to 0, right, gives us the answer. Okay. So if I now write A as amplitude R times e to the I phi, phi here is the phase shift, and plug it into this equation, and I'm skipping the details, then I finally obtain the equations for how the phase shift evolves. So for example, if I now solve this equation with the additional conditions R of 0 is equal to 1, then I obtain the following result for R of S. Okay. And what this says, right, is that if I plot R of S versus R, then I get the following. The origin is unstable, and the other roots are stable. Okay, so I get R of S, okay, approaches to this root 1 over square root of 3 as S goes to infinity. Well, it should be S over here. Okay? Okay, so finally, what does this all mean for the original equation? Let's just go back for all this change of variables that we've done. Okay, so first of all, I'll just say what happens as for at the long time. So after a while, as t goes, as t is large, as t becomes large, then we have this R approaches 1 over square root of 3. Now, remember that this R is the A, and the solution U was A e to the I phi plus complex conjugate. And so as we've seen before, that's equal to 2 times R times cosine of phi, which is just cosine of t. Okay, cosine of phi. Okay, and so this approaches to 2 over square root of 3 times cosine of t plus some phase shift. Okay, let's just say like that. Okay, as t goes to infinity. And now let's translate what that means for the original system in terms of x and y. And here is the translation right here. Okay, there's the x and y. So x is 1 plus u, but then u is epsilon times capital U, v is epsilon times capital V. So let's write all this down. So x is 1 plus epsilon times capital U, y is b plus epsilon times capital V, and in addition, b was equal to the Hopf bifurcation point, which is at 2, plus epsilon squared. Okay. So for example, if we now take b to be equal to, oh, and one more thing. What's the relationship between a u and v? Go back here. So from this equation here, we can see that v is u prime minus u, right? So this v is just u prime minus u. Okay, so for example, suppose that we take b is equal to 2.05. Okay, if we take that, then we have to compute epsilon. That means that epsilon squared should be 0.05, or epsilon is the square root of 0.05, which is 0.2236. Okay, 0.2236. Okay, so we take that epsilon, and now we sketch the solution for x and y and for b. And for that, I have a Maple spreadsheet, so I'll switch to that. Okay, so here we are. I've opened a Maple spreadsheet, so I'll type the equations in. There are the equations for the brusillator, and I'll take b equal to 2.05. Okay. Let me call those equations something. So that's ODE system. B is equal to 2.05. So Maple allows to easily solve it. I specify the ODE and some initial conditions. I'll just take whatever initial, like some, doesn't matter what you take. Let's just take some random initial conditions like that. We solve it numerically. And it uses Runge-Kutta 4-5 method to solve it. And then I can plot it. OD plot, solution, x of t, y of t. T goes from 0 to, let's say, 1,000. Maybe to 100. Points equal to 5,000. Okay. And there's my solution. If I plot it up to time 500, it still looks the same. Maybe I need more num points. Okay, so there's my solution. There it is. Okay, and so it approaches a limit cycle of this form. And so the multiple scale analysis should capture this. So what we found with the limit cycle is described as follows. So it would be x is 1 plus epsilon times u, and y is b plus epsilon times v. Okay. So now I'll specify what u and v is. So u is 2 over square root of 3 times, let's say, cosine t. V is derivative of u minus u. And epsilon is finally its square root of 0.05, right? In other words, b minus 2, square root of that. Okay. And so now let's compare these two things. And there is the comparison. Okay. So there's this blue line here is the analytical solution or asymptotic solution as predicted using multiple scales. And the red is the actual numerical solution. Okay. And so you can see a reasonable agreement. It's the blue orbit is slightly shifted from the red, which is not a surprise because epsilon is relatively big, about 20%, and this difference is of that order. Okay. So that's the power of multiple scales. We're able to predict exactly what happens beyond the Hopf bifurcation, and in particular, the dimensions of this nearly ellipsoidal orbit when B is close to the Hopf bifurcation value of 2. Here, B being 2.05. And of course, this works well even if I choose a different B. For example, if I just choose B is equal to 2.01, then this should work even better. Except now I'll take the epsilon, I need that to be B minus 2, square of that. In this case, it's 0.1. Yes, and you can see now it's even better agreement. It's hard to see here, but yeah, there. Okay, forget what's color shade. There it is. Okay,